And we can make sure I can get the mouse into the right place. Mouse is there.
I won't be using the mouse, so it's fine.
I just need to make sure that it's actually there, because if you're going to use the that's just a mobile mouse, right? The wireless one.
Yeah.
That's right there. You're not going to use it?
I will use that.
You're going to use that one, right? No, they're both mice. It's just this one's harder to steer.
Okay.
And I'll just stare at the clock and wait for it to turn to 8. See, the initial joke was that when we came in here, that clock didn't work, so it always said the same time. And so I would make a joke about it every single day. And somebody must have reported it because someone from facilities came and changed the battery in it, even though it's not an officially supported clock. All right, so it is 8 o'clock. We can get going here. Some of you might remember me, and I'm glad to introduce our newest faculty member here in the Department of Computer Science, Arpan Gujarati, and he tells me that he literally accepted the offer yesterday. So he literally accepted the offer yesterday. They haven't even actually, I haven't seen any announcement yet.
I think the head sent out an email yesterday.
I didn't see one, but I don't know, there's so much email now. So at any rate, Arpan's here and he's going to keep you amused by talking about fault-tolerant distributed real-time systems. Because, you know, distributed systems aren't hard enough. Fault tolerance kind of does go with distributed systems naturally, but the real-time aspect of it actually makes it even harder, which you've already seen how hard it is just to get it to work in non-real time.
Okay.
Thanks, Arpan.
Yeah, so if I understand you correctly, so far you have been learning and studying a lot about big data center systems, right? The problem is equally hard if you go down to embedded systems, which fit in one room or, as I say, on my office table itself. But that does not take away any of the challenges of building a distributed system, which are also fault tolerant. So I'm going to tell about my perspective on distributed systems and focus on one of the projects I worked on in the last 1 year. Think of this as applying some of the techniques you learned throughout this course. All right, so let me first start with what I mean by cyber physical systems, which is the broad domain that I work on. Now, a formal definition would mean that these are just computing systems, like any software system, but that are tightly integrated with the environment in the form of actuation, control, and physical sensing. So, unlike most systems, you would do on a periodic basis sensing of the environment, then do some computation, actuation, and then cause a physical change in the environment. Any simple example that comes to your mind, apart from the airbag that I have shown there, of a cyber physical system? Yeah? Yeah, sure. Driverless car camera. I was thinking something even simpler. So I have a figure of a plant watering system, which is a very simple cyber physical system that you can literally build, I don't know, in a few hours if you have the right equipment. All it does is that it checks the moisture of the soil every minute or two and decides to water the plant based on some decided threshold. So it's not distributed, it's not fault tolerant, but it's a cyber physical system. But that's not it, right? You have literally thousands of cyber physical systems. Some of them are very complex. You mentioned autonomous cars and cameras that fit somewhere within this figure. What differentiates these systems from the plant watering system is that these are safety critical, by which I mean that if they fail, it can be damaging to either human life or significant property can be lost. And that's why in the long run, fault tolerance becomes important. So I'm going to start by talking about one specific kinds of faults, low-level faults, which can trigger more complex fault scenarios. So the faults that I am interested in is environmentally induced faults. So in any system, think of any system you can, there are environmental interferences. Like you could have a solar radiation flare cause a bit flip in a hardware. Sometimes you can avoid these, sometimes you cannot. And what this does is that it can cause occasional bit flips in your memory buffers or networking components. Now, you might think this happens very rarely, that you may not have to take care or even think about it as a software designer, but that's not true. If you're designing a safety critical system like an autonomous car, you do have to think about these, at least to the extent that you can rule them out in a logical way. For instance, one of the studies recently from UIUC showed that about 5,000 vehicles per day can be affected by a soft error with potentially catastrophic consequences. So now that's a very high rate. So now the next logical question is, now that we have done this empirical study, do these soft errors actually lead to something important? Do they actually cause a kind of fault that you have been reading about in this lecture so far? And actually it does. For instance, it has been shown that transient faults can lead to a bunch of different error scenarios. I'm not going to define these. I expect you to understand all of these, but let me just ask you, uh, could anyone define omission faults for me? I mean, that's a one-line definition, but does anyone want to try elaborating omission faults in a distributed system? Yeah, and that typically happens when a bit flip causes a kernel panic. So one of the nodes in the system would go down for a while, and during that duration, there are no messages coming from that node. So that's a very classic example of omission faults. What about incorrect computation? You might know this from a different terminology, I don't know. Do you want to elaborate on incorrect computation faults or give me an example different from the one here? Yeah. Right. So think of the same thing as omission faults, but this time there was no kernel panic. Some memory just got corrupted, nobody detected it, so now you have something in your system that's not what was intended. Now, some field is incorrect, your program may end up using it, may not end up using it, that's a different thing. But you do have faults that go undetected, which are classified as incorrect computation errors. And finally, you have the most general class Byzantine errors, which I'm pretty sure you had in the course, right? Right. So here I say that Byzantine errors mean inconsistent broadcast in distributed systems. Is there any other definition that you learned? Yeah. Okay. Right. So you're right there. We are not looking at the malicious angle here, but essentially the meaning stays the same. You might have some form of equivocation in a distributed system, or one node sending different values to two other nodes in a distributed system. And actually, this is not just a theory, right? There was a very nice study from Honeywell, which is a big company in the US, builds defense equipments and all. We try not to be inspired from these companies in research, but this is a motivating example, so be it. So they showed that even due to environmental interference, so no malicious actors involved, there could be Byzantine problems in a real system. And actually, the probability of their occurrence is much higher than what practitioners believe. So this means that if you're designing a system that is supposed to be extremely reliable, you must address all these errors, because you are generally trying to shoot for a very high reliability goal. For instance, I have put a number here which says that probability of failure is less than 10 to the power minus 10 per hour. And these are the kinds of numbers that are thrown around when you read literature from avionics domain, or sometimes even from automotive domain. So how do we, the big question that I have been trying to tackle is, how do we go ahead building systems to address these kinds of faults? Now, obviously, we all fly in airplanes, they are safe, so they must be doing something, right, to handle these faults. And actually, what a lot of these systems do is they ensure that the hardware itself is highly redundant and fault tolerant. So this is one such architecture presented long time back, but it paved the way for how avionics systems ended up being designed. So it shows that in the hardware itself, you have custom redundant configuration. So you have a bunch of application processors which are denoted using AP, control processors which are denoted using CP. So application processors run the workload in parallel. They just run the replicas. And control processors continuously sync the states of the replica in a fault tolerant manner. So the hardware guarantees with very high reliability that the replicas never diverge. So at the application level, there is never a question of adding more fault tolerance. The hardware pretty much takes care of most of the things. And this is good in many ways because it gives you a very predictable blueprint such that you can then run mathematical analyses and come up with these kinds of numbers if you start with a probabilistic fault model. But this is not possible all the time. Like if today we start building a drone and we decide we want to make this drone reliable like an airplane, we cannot do these things. I cannot order a custom hardware, it will cost me a fortune. So that's the problem. When we talk about lots of cyber physical systems that are designed today, robots, surgical robots, automobile components, drones, they are designed and engineered using inexpensive off-the-shelf components. Think of any off-the-shelf embedded system like Arduino board, Raspberry Pi. These are commonly used in systems today. Also, the software is often open source. It's not as reliable. There might be other bugs. So the summary is that lots of cyber physical systems that are designed today are not equally reliable as airplanes. And that's maybe okay today because like I don't see 1,000 drones flying around me right now. But in the future, this might change. There will be so many autonomous CPS around us that if you consider a fleet of these devices, like think of a fleet of million drones. Across this fleet, I want the same level of reliability as I had for my avionics domain systems. And that is when it becomes important to design and tolerate all kinds of errors. So the goal of my research so far has been basically to come up with software systems design for these kinds of inexpensive cyber physical systems, which can address different kinds of faults. So in short, how can we address these faults in the software on the common chips that we see around us? And I mainly care about two properties. I already told a bit about fault tolerance. The second property that I care about is real-time computing. Now, does anyone have an idea of what real-time computing is? No? So, real-time is a phrase that's thrown around so often these days, right? You have startups saying we will deliver messaging in real time, prediction in real time, automated chat responses in real time. So generally it means that doing something in a way that humans can interact with. But here it literally means doing it in a way that environment and physics can interact with. So you're designing a software loop that interacts with the physics of the environment, and this could be at a granularity of few milliseconds. So think of an airbag. You have crash sensors continuously detecting a crash, and when they detect something, they need to issue the command literally in a couple of milliseconds. So which means that you need to be pretty sure that your software is going to finish this sensing, computation, and actuation loop within a stated threshold, which is called a deadline. And if this is missed, then it's called a deadline miss, and it can be dangerous. And the entire field of real-time systems, which is probably thousands of people in the world, they work towards ensuring that both mathematically and from a software design perspective, your software is running on time and your hardware is predictable. So you want not only good design, but mathematical proofs based on the model of your software design to show that an algorithm will never cause a deadline miss. And this is what makes the problem difficult, a combination of timing requirements and fault tolerance. So now let's get into the main parts of the problem, right? So I want to solve the problem of fault tolerance for cyber physical systems while taking into account real-time properties. Why can't I use something that's already existing? Why do I need to design a new solution? So I showed you what avionic systems do. They use custom hardware. They give us a bunch of good properties. They give us Byzantine fault tolerance. They give us timeliness because it's in hardware, so it's very predictable. But it's not low cost, so we cannot use those solutions. Then there are some of the systems which you might know or familiar with from this course, right? Redis, etcd, Zookeeper, bft smart. These are all research slash production systems that are designed for distributed data stores or generally distributed in nature. They have some form of fault tolerance incorporated, and we can incorporate these systems inside the real-time systems or the cyber physical systems domain. Now, they will allow us to design Byzantine fault tolerance, most of them, but they do not have real-time predictability, by which I mean that it's pretty easy for a system like Redis or Zookeeper to miss a deadline. It won't care about deadlines at all. It will run on its own speed. On an average case, it might do well, but in the worst case, it's going to take a long time to finish an operation. So this may not work. I can look at some of the open source software that is designed for real-time systems, cyber physical systems, drones, robots, like robot operating system. Ardu Pilot is a open source firmware for drones and quadcopters, I think. But they don't care about fault tolerance, and which is why in this work, what I'm going to present at a high level, I have designed a distributed time-stamped key value store, which I call Achal, which tries to address each of these properties. Any questions so far? Yes. And I had a look at the project, and I think that's the overall goal, right? Design a key value store. Yeah, sharded key value store. Okay, so next few slides are going to be very easy. Basically, so now I'm going to answer three questions, right? What, why, and how. So, what is the key value store? What are the semantics? Why do we really need them? Need a key value store API for control applications or cyber physical systems? And then, how do I actually address some of these properties? So, let's start with the first question. What are the key value store semantics? And this is probably very easy for you guys because you have already implemented it. Uh, so here's the API for the key value store. Does this look familiar to you guys? Or is it different from what you have? You have get and put, but with the same interface. Also the same return value, sort of. Okay. So here's a question. I don't know if you guys had a time to think about this, but what are the benefits of key value store API? I have listed a couple of them. What do you think are the benefits? But why do you need a key value store API? I could have a shared memory system. I'm talking about the API. There are lots of APIs. There's a publisher subscriber API. You can have shared memory. You can have message passing. Why? What's the benefit of key value store API? Okay. Anything else? I mean, you should have some answer if you're building a key value store. Because when I did my distributed systems course, I didn't build a key value store. I built a file system. I know it's the same thing, but it had a different interface. So yeah, right. So exactly. So I think for me, it basically simplifies programming, and that's the only way to look at key value store. That's nothing more or fancier than that. It pen append, right? Right, right. That makes sense. So sometimes key value stores can also be good for data sharing. Like, forget about faults, but some of the systems are inherently distributed. If you think about the ROS I explained a while ago, the robot operating system, then the way it's designed is that you have different components talking to different actuators on the robot. Like you can have a gripper on your robot, and you can have a software library controlling the gripper. You can have a vision module that's controlling the camera on the robot. Now, these libraries are developed separately by separate people, but they can expect that there are other components on the system. So they basically use the key value API inherent in the robot operating system and basically ask them, is there a value for this particular key, a gripper key? And so some of the systems, it simplifies the programming a lot, especially when people are dealing with such inherently distributed systems. All right, so I'm going to make one small change to this API. I'm going to timestamp this, which means I'm going to have a time parameter for the read and write. Have you looked at any papers that looks at timestamp databases by any chance? No, right? Okay. So what does this do? What does the time parameter mean here? So first of all, I'm going to treat it as an absolute time parameter. And here's the definition. So if you are reading a key and there's a time parameter t, then it's basically imposing a constraint on the key value store that return me a value that's not older than time t. And if you do not have any such value, then fine, return me a time error or whatever. Similarly, on the right side, I'm going to treat it as a commit time or a publishing time, which means that ensure that value v, which I'm trying to write for a key k, I want to ensure two things. First, make sure that this value is not public before time t, because I don't want anyone to read it before time t. But at the same time, somehow guarantee that all nodes have this value locally available before time t, so that if someone wants to read it after time t, they do not see an error. So any doubts here? Any questions? Sort of. At least in the theoretical model, yes. Any questions on the API? Okay, so one way to simply think of it is that the union of key and time makes a unique key, and that's an easy way to implement it in your system. All right, so can you think of any benefits of this timestamped key value store API? Where could this be useful? But why do you need time for that? You could just have a version number. Yeah. Sorry? Yes, but except that in some systems you do care about the absolute time. So I had two examples. One was financial markets, where you literally want to put a query based on some absolute times. And second is sensor data in cyber physical systems, where let's say you are reading something, you are executing a code at this time. So right now, I I want to say that give me something that's not older than 20 milliseconds. So now I cannot add this query in the form of versioning unless I know the mapping between version numbers and time ranges. So it's easier as a programmer for me to say, give me something that's not older than 20 milliseconds, or I can also translate it in absolute timestamps that something that's not older than now minus 20. Similarly, I can, now this is important, I won't go into detail, but this is important for verification. If I'm writing something, I want to say that I know that my system is not extremely fast. It can only guarantee writes will propagate in the next 20 milliseconds, not faster than that. So it's possible that some system may get the values faster than 20 milliseconds, but by and large, I'm guaranteeing that my system will only commit all values across all nodes in 20 milliseconds. So I want to say that do not make this value public before now plus 20. And this means that all my nodes are going to see data that has the same age. And this is important. Age of the data is very important when designing many cyber physical systems. And when you are verifying, you want different nodes to have consistent age of the data. Right, so we have KVS, key value store API, we have timestamp key value store, and the next step is very logical. We are going to have distributed timestamp key value store. So this is simple, right? All we have is key value API on different nodes talking to some application, and all the nodes are connected over Ethernet. And this is the high level system that we want to design now. Now, okay, before we go further, I can ask a similar question. What are the advantages of a distributed timestamped key value store? Or rather, what are the advantages of making this whole process distributed? Yes. Right. So we have hardware fault tolerance. We can tolerate crashes or other kinds of faults. And I think that's pretty much it. Some applications may be distributed, like I mentioned. So they do require multiple nodes. Sometimes you care about fault tolerance, so you need a distributed system. So yeah, not much novelty there. All right. So now we have a high level idea of what we want to build. So let's get into the second part, which is what was it? What? Why? Why was the second question? So for the kind of applications that I am looking at, why is this API useful? So I'm going to start with one example. So this is an inverted pendulum pseudocode. Does anyone know what everyone know what an inverted pendulum is? No? Okay. So if I try to keep this remote stand here, it will, I think it will fall. So this can be called as an inverted pendulum, but I want to balance it. So you might try to balance it by moving your hand continuously. So that's what an inverted pendulum does. It's a vertical rod with a mass on its head, and on the bottom there is a small cart which is fixed with a motor for a horizontal movement. So now the goal is to give just the right velocity to the right horizontal motion to the cart such that the rod remains balanced all the time. So it's a very classic example because it's a system that requires some command all the time. You cannot ever leave it in an idle state, otherwise it will fall. So you need to continuously keep on measuring the angle, which you can do using different ways. There are magnetic sensors, there are camera vision sensors, there are different ways to measure the angle. And then you have a motor controlling the horizontal force. So what you need is a compute logic to map the input, which is the sensor value or the angle sensor value, to the output, which is the force that needs to be applied, right? And actually you can write the code for such a system in less than 50 lines of code, I think, I'm pretty sure, because there are many solutions, but one way is to just look at the current value of the sensor. So current difference from 0, is it 0 degree, 1 degree, 2 degree, and then compute a bunch of error values. You compute the absolute error, you compute the integral error, which is the cumulative error over multiple iterations. You can compute the derivative error, which is the difference between the current error and the previous error. And then in this code, what I'm using is called a PID controller. So this relies on three constants, P, I, and D. So you can train these numbers beforehand, and you can then apply these constants and multiply each of them with the respective error values, like I do in line number 7, and compute the force. And this is called a classic PID controller. It's one of the most well-used controller in so many systems out there. So this is a very simple system. It works magically, but it's not fault tolerant. So how can you make it fault tolerant? You might want to add one more compute node so that if one crashes, other can take over. You might want to add yet another compute node so that if two compute different answers, then you can apply some voting, because two nodes are not enough to tolerate incorrect computations. You cannot vote on two values. You need at least three values to vote. And if you really care about Byzantine fault tolerance, you may want four nodes. Yes, so when I say multiple nodes, then it can translate into each node having their own sensors, or one sensor that sends values to all nodes. These are both valid models. It depends on what's feasible in the system. Now, in a system like this, if I'm going to add a magnetic sensor or a camera based sensor, it's very easy to add multiple. But when it comes to motor, there can only be one motor for the cart. So what I can add is multiple signals going into the motor, and I can add a small chip. So typically what it's called a guardian node in the literature. Guardian node is the trusted small hardware unit whose job is to get all the redundant values and then map it to one output. So think of it as clients in your distributed protocol who expect don't know, n minus f or n minus f inputs to work with. Right. So I'm going to think of this extreme configuration where we need four nodes. I'm going to do replica coordination like in the most critical systems, and which means I'm going to figure out what are the important variables in my code which are propagated across iterations. So these are used again and again and they keep on changing. And what I want is that all replicas start with the same version of these variables all the time. And the only way to do this is to do frequent continuous replica coordination between every iteration of this function. And this function runs in a periodic loop. So depending on the application, you may want to invoke this every millisecond or every 10 milliseconds, whatever is the frequency that suits the application. So you want to do replica coordination between every consecutive iteration. And this is non-trivial for control systems developers because they are not distributed systems engineers, they are not network engineers, so they might not know how to manage this replication. So which is why a key value store is useful. So this is the same function where I have replaced some of the lines with the key value API. I'm reading some values from the key value store. I'm writing them back at the end of my application. And every time I have a time value T1 and T2. So I start with the T1 in line number 2, which is time of the previous activation of my control loop. I'm going to ask the key value store, give me the values of these parameters that's not older than T1, so not older than one iteration. Depending on the application, I can make this not older than 10 iterations. And then once again, when I'm done applying or computing the force, I'm going to write all the values back to my key value store so that before the next iteration, all nodes get a chance to sync with each other and decide what are the starting points for the next iteration. And at high level, this simplifies, the API simplifies replica coordination, and as I said before, it helps with temporal verification. So, any questions so far? Yes, they are calculated locally here in this case. So these are just absolute timestamps, so you can use your local clock. And yeah. Yeah, so I guess your question is at a high level understanding what does these timestamps mean across the distributed nodes. Yeah, so I guess that brings to me to the next point, right? No, not really. We still have time. Right, so you are hinting at some form of clock synchronization, and which is an important assumption in my system, which I'll come to in 3 slides. Right. Any other questions? Yeah. Yeah. Yeah, that's one of the design goals. You need to design the system such that you can take these requirements and then make sure that those are actually enforced. Exactly, exactly. Yeah, yeah, you can enforce these kinds of semantics. Yeah, right. So I just want to emphasize the point where I say that these functions are periodic in nature. So for instance, on a regular basis, so this is a diagram, schedule diagram as I call it. On the x-axis, you have time. This is just one node, not a distributed system. On the x-axis, you have time. These gray rectangles are executions of the function I showed before, the inverted pendulum code. So in the beginning, they read some values from the key value store. At the end, they write the values back to the key value store. And when the function is invoked again, it does the same thing again. It reads a value and writes the values. So what we want is that we want the key value store, which might be running on a different core or on the same core, to execute somewhere in between these two consecutive iterations. And it must finish the coordination with other key value stores on other replicas strictly in between these two executions. Make sense? And this is easy if you have just one application. Like executing these two functions are it's fine. It becomes more difficult if you have more applications with different frequencies. So now I have another application which runs at roughly twice the frequency as the first application. So it's going to invoke the key value store more often now. So I need to design my process of key value store and schedule it such that it executes at least once between any two consecutive iterations of each of these applications. Does that make sense? And I can make this more complex. I can have a very high frequency application. So now there are a couple of things happening here. If you see some invocations of key value store, they need to read keys or they need to service the read request from three different applications, like the one in between. Whereas if you look at the second execution of key value store, it needs to service request from only one application. And this means that the workload for the key value store, every time it is invoked, is different. And this affects the predictability of the system. Like, how do I know how long does the key value store take every time it is invoked? Sometimes it might take, if it has a workload of 10 reads and writes, it might take 20 milliseconds. If it has a workload of only one read and write, it might take just 2 milliseconds. And of course, things get even more complex once we start figuring out that the coordination actually involves a networking component. So the request need to go to another node over your Ethernet network. So how do you schedule packets on the Ethernet network? Are those packets coming back on time? Is your networking schedule predictable? So it can keep on getting more and more complex. But at high level, there are two questions in front of us. One, okay, first is the question of Byzantine fault tolerance, for which there are lots of answers out there. You read some of them in your course, which is what goes inside that green box of key value store. What is the coordination algorithm that we are running? And second is how can we design the implementation of whichever algorithm we choose such that we can guarantee the execution completes before the next iteration of the application starts. So we need some guarantees on the timing of the execution. Make sense? Right. So I'm going to talk about 2 or 3 high-level principles here about the implementation and not go into more details. The first building block is, like you said, clock synchronization. And at least the way we are looking at the system, it's inevitable because we want some way to make sense of the publishing times across distributed nodes. Now, did you guys use clock synchronization or study clock synchronization in your course?
A little bit.
Little bit. Can you use it in a distributed system? Well, like, what are the trade-offs when you use clock synchronization in a distributed system?
We did talk about Google Spanner.
You talked about Spanner.
We talked about Spanner.
Okay, so does anyone remember what kinds of guarantees does Spanner provide? Or in other words, what is the granularity of accuracy I can expect from the global time in Spanner? But what are the typical values of delta? How small? Okay, I don't remember the number. Yeah,
I mean, NTP is giving you what, 10 to 30 milliseconds typically, up to
yeah,
100 milliseconds.
yeah.
But
So you
Google Spanner
typically
is closer
get
to like
in the
what?
order of few milliseconds
Yeah.
when you design any such API in a data center style system. But here your execution frequency might itself force you to run something every millisecond. So you want guarantees one order higher. So you want guarantees in the order of microseconds, which is not possible in data center style systems, or maybe possible in a few years with custom hardware, but not with the regular hardware. But in an embedded system, it's very much possible. If we use, so there's NTP, network time protocol, but there's also another called PTP, precision time protocol, which is commonly used in embedded systems. And this can allow you or guarantee you microsecond granularity clock synchronization accuracy just out of the box. When I say out of the box, I mean I'm using software timestamping. I'm not even using custom hardware. If I use a custom clock source or specific Ethernet switches, I can get like in a granularity to the order of couple of microseconds, not even 100 microseconds. So the high level point is that different domains have different constraints. In embedded systems domain, you may not always want to assume that there is no clock synchronization. You can start very well from this assumption and then figure out, okay, what are the limitations? Where does this assumption break? So it's a very valid assumption to make in this domain. And obviously, this simplifies Byzantine fault tolerance, right? But in what way? Anyone want to elaborate? How does clock synchronization simplify fault tolerance? Does it make anything possible that was not possible before? Yeah. Across? So consistency of? Right. So you can design protocols where you can expect that if something is not arriving on time, then it's pretty much failure. You don't need to wait for an infinite amount of time to wait from correct nodes for anything. And I assume you did read FLP. Yeah.
We've talked about it over and over again.
Yeah. So the classic proof in distributed systems that consensus is impossible in general, but you can make many different assumptions. One such assumption is clock synchronization, which can let you make it possible. Right. So There are thousands of papers published on this topic. So
Hmm.
this paper is not about coming up with a new protocol or my work. So we are just going to use an existing protocol. For me and for this particular domain, there were a few key properties that we were concerned about when choosing a fault tolerance protocol. So first was, since we made an assumption on clock synchronization, we wanted a protocol that made use of it. So we chose a synchronous protocol for fault tolerance. But an important aspect was that we wanted a leaderless protocol. So among all, so you guys probably studied protocols like Raft
We've talked about
or Paxos
quite a
and
few
all.
of them.
So a lot of distributed systems protocols have a leader, and it goes through leader election when something fails. This is a standard approach in classical distributed systems. It does not always work in cyber physical systems because the latency for leader election often becomes a bottleneck. So you want a leaderless algorithm, which does not rely on one node being the leader. So there's no performance bottlenecks as such. And that was an important criteria. And here I say higher reliability, which is basically when you mathematically model the system and you start with a probabilistic fault model and then quantify the reliability of what's the probability of this node failing and this protocol failing and so and so. If you have a leader based system, because there's a bottleneck, your reliability quantification will come up with an answer which is very low. Like a system reliability is low, but in a leader based system, mathematically you can say that the reliability is going to be higher. The third point is interactive consistency. Now, I don't know if you read this term, but you can essentially map the consensus problem in three different ways. There is this Byzantine generals abstraction, there is a consensus abstraction, and there is an interactive consistency abstraction. So the difference is that in each case, who is proposing the values and how many values you need to agree on. So I can use the whiteboard here.
If you write it over here
Here
behind the laptop, it'll actually show
behind
up
the
on the.
laptop. Okay.
Yeah, if you write it right there,
Okay.
it'll show up
So
on the.
typically you have value v1 proposed by node n1, value v2 proposed by node n2, value v3 proposed by node n3, and so on. And the goal is to agree on some. The goal of consensus is to agree on one value. Interactive consistency is slightly different. Nodes propose these values, and the goal is for every node n1, n2, n3, and n4 to agree on a final vector v1, v2, v3, v4. So every node should agree on the final vector, each element of which is the value proposed by each respective node. Essentially, I'm not throwing away individual values. I'm carrying forward all values, and formally this is equivalent to the consensus problem. Or you can think of it as doing 4 rounds of consensus. But this is useful because when you are dealing with noisy sensor values, you may not always want to apply majority function to resolve your redundancy. There are lots of very application specific metrics that you want to apply to this vector. So you start with this goal, and then you can let the application decide what it wants to do with this vector. It can apply a very complex averaging function or some fault tolerant median voting functions. There are lots of them out there in the literature. But that's also one of the requirements we had in this system. So this particular protocol, EIG-BIS, so it's an implementation of a very old protocol. So there's a very famous protocol from Lampert, Shostak, and Pease from 1980, which solves the problem of synchronous leaderless interactive consistency in the presence of Byzantine faults. And Boran and Schreiber recently basically gave a good, I wouldn't say an implementation, but a good algorithm to map that protocol to a specific set of execution steps. So I use a combination of these two in this work. And actually it's a clean and nice paper. so feel free to read it. It goes beyond clock synchronization actually. It actually shows how you can implement a leaderless protocol in a partially asynchronous system with some extra rounds. Right. So we have two building blocks that allows us to design a distributed protocol. And now the timing problem, right, which has nothing to do really with distributed systems, but this is where my research comes into picture or my area of work. Uh, so here is the very high level thing what we do. We know that control applications are periodic, which means they arrive precisely at a specific time points, like every 10 milliseconds or every 15 milliseconds. Also, their execution times can be bounded. So we know precisely what they are running. So the execution time of the inverted pendulum function can be easily bounded both on the lower bound side and on the upper bound side between, I don't know, 100 and 150 microseconds, for instance. So we have this nice guarantees on control applications. So what I'm going to do is that I'm going to also make my key value store execution periodic in nature, which means I need some way to reason about the worst case execution time of my coordination protocol. So remember I told you earlier that sometimes it needs to service 2 reads and writes, sometimes it needs to service 10 reads and writes. I'm going to make an estimation of all the applications running on my system and figure out in the worst case how many reads and writes does it need to work with at any point of time. This is possible because my workload is deterministic. So once I have that answer, I'm going to do some empirical profiling to figure out the execution time of my coordination algorithm. This is taking into account all the time that goes into network messaging, the messages over network. And then obviously, I have ton of optimizations to make sure that my implementation is highly predictable, which means that I'm not doing anything to improve the average case scenarios. I'm doing at every step, I'm considering what's the maximum workload or maximum queue size, and then I'm taking that into the consideration. So I get a number here out of this exercise, which is expected to be a very high confidence number on the execution time. Now, once I get this number, the second question is, how often should I execute my key value store function? The simple answer is that it should be faster than all my applications. But how fast? If I execute it very fast, it means that I'm essentially scheduling or provisioning my CPU to run key value store more often than required. So I'm essentially wasting CPU cycles. I don't want that. So this is where all the mathematics of real-time scheduling theory goes. So mathematically, you can figure out that these are my application execution diagrams. These are the empty blocks, as I showed before. This is the execution time of my key value store in the worst case. So what's the smallest? I can just feed this question to a model checker, which will give me an answer. What is the smallest time period or the arrival time between consecutive iterations of the key value store that I need that satisfies all my constraints? And the model checker can give me an answer. Or I could use, now model checker has limitations. It might not take into consideration all the complex scheduling policies. So I might use some mathematical analysis from real-time scheduling theory, which I do in this case. So I won't go into the details of these right now. They are not relevant, but the main point here is that what we have ended up doing is that we have designed a distributed time-stamped key value store that is a function of the workload and the platform. So unlike in data center systems where the workload is highly dynamic, you have application requests coming in. Sometimes you have more workload in the daytime than during the night time because more users are working in the daytime. There are no such constraints here. Workload is extremely predictable. You pretty much know what are the applications running on your system. So you are able to map the configuration of the workload to the configuration of your key value store. And it's also a function of the platform because all the execution time profiling I do is a function of my hardware and the resources I have. So I'm able to optimize my system as much as possible to make the best use of my hardware resources for my workload, which is known a priori. And in short, this is also one way how a lot of cyber physical systems development differs from other systems. You often try to make the best use of your resources, which are fewer, and sometimes there are power constraints, CPU constraints, so you don't want to use everything you have. You might want to switch off few cores just to save energy. So these kinds of problems and solutions help you do that. So I have, how much time do I have?
We have until 20 after, technically.
20 after 10. Okay,
Yeah,
that's
skip
good.
time.
I was thinking 8 or 9, so okay.
It's
good.
actually a, what is it, 80-minute class.
Okay. Right, so one thing we often do in research projects is that we do an evaluation. Because we start with the hypothesis, then we build a system, and then we want to verify, is this actually doing what it's supposed to do? Is it actually doing better than what other systems are doing? Do you generally read papers in this course?
I give them papers, and but we don't actually discuss the papers in class.
Right. So if you have read some of papers like Spanner, for instance, they would have an entire section on evaluation. So I'm just going to present one data point of results that I did with my system. So here is what the setup is like. We had two clusters of Raspberry Pis. I used just one for my experiments at a time. I had redundancy even in my cluster configuration because if one goes down, I can use the other for experiments. Now, this is my platform for Raspberry Pis with connected over some Ethernet. Now, the important question was, I have built the system called Achal. What do I compare it against? What is an identical setup? So the goal was not really to compare the fault tolerance in this experiment, the fault tolerance property, because we know we are getting those from the protocols. The goal was to actually evaluate the performance, the timing properties. So one baseline was Redis. Does everyone know Redis, or is it new to everyone?
We've talked about it.
We talked about it? Okay. Redis is a key value store. It's written in C, so generally considered good for embedded systems. You don't want something that's written in Java, which has garbage collection running at random points of time.
Nobody likes Java anyway, right?
So Redis is also designed to run on a single core. So it is very much designed, like I didn't talk about this, but even our system Achal runs on single core at a time. So if you want multiple instances, you want to run them on every core separately. So Redis is in a way very similar to our system Achal. So that's a good performance comparison. etcd runs is a good fault tolerant system. It runs the raft consensus behind the scenes, so it does all kinds of fancy communication. So that's a good fault tolerance baseline. And in the results I'm going to show you, we started with a very simple workload where we ran the inverted pendulum simulation like I showed before. Each task or each function reads and writes about 20 floating point values to the data store. And all we want to ensure is that we want to use one of these baselines to coordinate all this data between two consecutive iterations of my inverted pendulum simulation. I use a simulation because I don't have a physical inverted pendulum. So the simulation simulates the physics of the inverted pendulum. Right. So here are the results. There are lots of different configurations I tried. We tried a single core configuration and a 3-core configuration. So Raspberry Pi has 4 cores. I left one core idle for clock synchronization and network functions, and 3 cores for running the application workloads in the 3-core configuration. Then we changed the workload quantity also. So we have a simple configuration where only one application is running per core, so one periodic function. We have a more complex configuration where we have 4 periodic functions running on each core. That means 4 times the amount of work to be done. It's just scaling up the amount of workload for the baselines. And then we have the period So period is the time between two consecutive activations of the periodic application. So I decrease the period from t equal to 800 to t equal to 50 milliseconds. So the highest frequency application required running every 50 milliseconds. That means the coordination should happen between the two consecutive iterations. And actually, if there are multiple applications running, it might even need to be done more frequently. So these are different configurations, and on the y-axis we have our evaluation metric, which in this case is there are two metrics. One is the successful read metric percentages. So we measure the percentage of iterations during which all reads were successful. So let's say the inverted pendulum code is reading three values in the beginning. If even one of the values returns a timing error, I'm going to say that that iteration failed from a read perspective. Similarly, for the writes, I measure the percentage of iterations during which all writes were successful. So at the end of the function, the application wants to write three values. If the key value store returns failure for any of the writes, I'm going to say that the iteration failed. So here are the results for my system. Now this is such a carefully designed experiment that I do not show any failure of my system. That's a sign of a very bad researcher. But I'm going to show only one result here, so let me show you the good one, right? Okay, so our system has good success rate everywhere. So we don't care about writes because if you're writing something, at least the way our system is designed, it's going to take that value, say thank you very much, and that's all. What we care about, so writes are always going to be successful. It's the read which is important. When you're trying to read something, if the previous write didn't propagate the values on time, your reads are going to fail. So we care more about reads than writes. And the good thing is that reads are also successful in our system. Okay, I was meaning to bring them one at a time, but something failed in the animation. So, okay, we have both the results at the same time now. So one is Redis, which is in blue. Redis is generally doing good when I equal to 1, so we have less workload. But when the workload starts increasing, Redis starts like performing slowly, so it does not finish its work on time. It's not even doing any fault tolerance. It's still slow. etcd is doing fault tolerance, and as a result, when you ask etcd to write something, it immediately goes on and talks to other nodes and does all the synchronization, runs the RAF consensus algorithm, and only then it returns a success. Which means not only do writes fail, but the subsequent reads also fail. etcd is probably the worst performing baseline here. And you don't even see some of the bars here because it just didn't stop reacting. Okay, so we actually, now you might be thinking why these configurations are useful at all, right? Why I have certain numbers of C, I, and time periods. So actually, this is a simple version of a more complex workload. So we borrowed a workload from Bosch. Bosch is a company that supplies chips and solutions to automobile companies mainly. So they had published a workload, a distributed workload, which consists of about like thousands of small functions, periodic functions, running on different nodes and talking to each other using key value API. So their functions are basically a mix of different frequencies. So some have time period 800 milliseconds, some have time period 50 milliseconds. Sometimes they run multiple functions on the same core, sometimes they run just one function on one core. So the Bosch workload was essentially a combination of these different configurations, but 10 to 100 times more complex. And we actually saw similar results even in that workload. But we clearly see in the Bosch workload that if you try to scale it further, like there is a factor which allows you to scale the workload, it's very clear where Achal's performance is 100, and then it falls very sharply because that's how the system is designed. It's designed for a workload that you know in advance, and it's designed to guarantee everything 100% all the time. But if it fails, then we don't guarantee anything. It's better to not use it in that failed configuration. Uh, right, so what else do I have? Okay, I think that's good. We are on time. So I just want to summarize the key takeaways from this work. First is that interplay between timing and fault tolerance is non-trivial from what I have experienced so far in my work. Because at a high level, when you're talking about fault tolerance, you talk about logical correctness. In real-time system, something happening on time is also a sign of correctness, and something not happening on time is a sign of failure. So you have a second notion of temporal correctness, and you want to work with both at the same time, logical correctness and temporal correctness, which makes both designing and verifying the designs of the system more difficult. So I mainly talked about the design, but there is a whole aspect of verification, and you want to ask questions, right, to a system. How often does the system fail? Can I add one more control task without affecting the timing of the existing system? And you want to answer all these systems before you deploy it. So this is essentially a certification issue. And this is a second class of problems that makes the whole problem domain interesting. So these are the two main takeaways. You can obviously read more about all this in this paper that I published in 2022. And that's it. And if you just zoom out further, then I mainly want to point out cyber physical systems research, which is not about engineering systems, but about developing foundations for these kinds of systems. So you want to develop foundations for designing safety critical cyber physical systems, which require dependable, high confidence, and a lot of times provable behaviors. And this means a combination of work on runtime mechanisms and analysis techniques, or formal analysis techniques. So if you're interested in any of these things, you can send me an email, or if you have more questions on this lecture, you can send me an email, or if you want to work with me, you can send me an email, because I will be a faculty starting July 1st. And yeah, that's it. Thank you.
Awesome. Does anybody have any questions?
Yeah. So as of now, we do not have hard timing guarantees over network. So we have, it's a locally connected system, so it's not connected to the internet. And we precisely know, well, I wouldn't say precisely, I know what's my application using the Ethernet for. Linux is also doing a bunch of things that I can try and control. As of now, I'm not doing, but that's the goal. You want to have the network which is more or less predictable. And the right way, like for me, the next step would be to understand, okay, let me replace Ethernet with something called time sensitive networking, or it's an Ethernet standard used for automotive domain. So it has priority levels, and you can limit the rate at which something low priority is being sent. So you can add these constraints on the Ethernet channel. So that would allow you very high predictability on the network. And there are tools which will just tell you what is a guaranteed round trip time for a message or one-way time for a message. So yes, that is a limitation of this work.
That's why there's still more research for you to do. So, I mean, I think it's a nice crossover. This is why I thought this would be a good lecture, because this is a nice crossover. We've been talking about distributed systems and consensus protocols and whatnot, and it's been fun to have different people come in and talk about ways that these actually get used in the real world.
Yeah.
And so while your work was based on these Raspberry Pis, your observations are, your workload came out of the automotive industry. You've talked about some of the things, like you talked about drones. So it's clear that this kind of work could be extensible, although you're not.
Yeah.
That was a great question, because you're not going to have Ethernet cables hanging out of your drones. You're going to be using
Right,
some sort of
but
Wi-Fi communications
no.
or
But
Bluetooth or
what
whatever.
you would have ideally, you can have a system of two to four chips on your drone itself,
Right.
which are all connected to each other over local Ethernet.
Yes,
So
exactly.
you're running an embedded distributed system on your drone,
Mm-hmm.
and that is where a system like this would be useful. Because I mean, drone is typically not controlled from the ground for all the critical functionalities.
No, I can't.
Right, right.
You just you don't
So you
you
would
don't
have this whole system
right.
on the drone for fault tolerance.
You want a self-organizing swarm, basically. That's where Byzantine behavior
Yeah,
starts to
but
become
swarms
interesting.
again.
Yeah,
You're talking about multiple drones, right?
right.
Right. I'm talking about just one drone and how the system inside that drone can be made fault
Within
tolerant.
itself.
Yes.
Okay.
Right.
Interesting. Anybody have any other questions? Well, if you do stick around UBC, obviously you'll be hearing about Arpan's work as he gets his feet into research in, what is that, 2.5 months now? Yeah,
Yeah.
so he gets 2.5 months to finish goofing off doing.
Although I think I'm planning a vacation on the day I join. I might go off on the first day.
Perfect. Just start using that vacation time right away.
Exactly.
Excellent, awesome. Well, again, thank you, Arpan.
Thank you.
And I will see you on Thursday.